All right, people, good evening and welcome to Analog Electronic Circuits. This is lecture 11. So, in the last class, we were looking at the basic negative feedback loop, where you have a feedback block, you have a forward amplifier, this is Vi, this is Vo, and we said that Vo by Vi is 1 over F times this quantity loop gain by 1 plus loop gain, where this loop gain is A times F and is physically interpreted as the gain that you get when you break open the loop, excite one side and see what comes back on the other side, and what comes back is A times F in magnitude and must be in the opposite direction. The opposite direction is needed for negative feedback, right? And as we said, an analogy for negative feedback is, is like the legal system in any country. If the laws are strict and the implementation is strict, then people will tend to commit fewer crimes. Okay, and so if AF, the loop gain tends to infinity, then the error voltage VE by Vi is nothing but 1 by 1 plus loop gain, which is again loop gain is A times F. All right. So, if loop gain tends to infinity, it basically means that the error voltage is 0. So, that again coming back to our social analogy, it basically means that if crime in society is 0, it does not mean that people are honest, right. It just means that the laws are so strict that the penalty for being dishonest is so high that you dare not commit a crime. All right. So, that is the just like how the error voltage is 0, right. The error voltage is 0 because the amplifier gain, that forward amplifier gain, is infinite. The moment the amplifier gain becomes small, that error voltage is no longer 0. All right. And under the condition that you have a very large loop gain, the closed loop gain, right, which is Vo by Vi, as you can see, is largely independent of the loop gain itself, correct, and the closed loop gain is simply 1 over F and is governed by the feedback block. All right. So, it turns out that this this is a great way of realizing amplifiers with very stable gain. For example, let us say you wanted to realize a gain of 2. We already have seen a common source amplifier, its gain is some minus Gm times RL, and nothing prevents us from choosing RL equal to 2 over Gm, so that you get a gain of minus 2. All right. But what are the problems with this this kind of amplifier? Well, temperature changes, Gm will change, which basically means that Gm RL will change. Okay. And so, therefore, this way of realizing gain is not robust. Okay. Now, if we realize that using negative feedback, if we wanted to realize a gain of 2 using a negative feedback loop, what should F be? F should be half, correct. So, if F has to be half, what is the easiest way of getting F equal to half? You just basically use a potential divider. Now, if temperature varies, what comment can you make about the values of the resistors? The values of the resistors will change, but we are looking for a resistor ratio, and therefore, even though the individual resistances change, both of them will change in the same manner, and therefore, the ratio is very robust, even though the individual values of the resistances are not. Okay. So, therefore, the situation boils down to, because we have if we are able to realize a negative feedback loop with a large loop gain, then all that we need to do to make the performance robust is make sure that the feedback block, whatever it is, okay, its properties are very well controlled. And fortunately, if you want a closed loop gain, then the feedback factor must be smaller than 1, which is easy to realize using some kind of passive element. Okay. And the forward amplifier's gain, which is needed to be very large, right, it must be it will be realized using some kind of transistor network. The transistors and networks of transistors, as we will see going forward, are very good at giving you a lot of gain, but that gain also changes a lot over temperature and supply voltage change and all that stuff. Okay. So, but fortunately, as you can see, thanks to negative feedback, if that gain is large enough, the sensitivity of the closed loop gain, right, or the input output VO by VI to changes in the gain of the forward amplifier is actually very, very low, right. For example, if the loop gain is 1000, okay, what is the closed loop gain? It is 1 over f times 1000 by 1001, right, which is 1 over f times 0.999. Okay. Now, let us say the loop gain for some reason went down from 1000 to 500, right. That is a either a 50% change if you want to be conservative, or it is a 100% change if you use a different denominator. You can see that you have a huge change in gain, but the closed loop gain is still 1 over f times now 500 by 501, which is only changes in the third decimal place. So, a 100% change in the gain has only changed the closed loop gain by some point something percent. Okay. All right. So, so just like money, if you have enough of it, then you do not have to worry about it, correct. Just like that, in a negative feedback loop, if you have enough loop gain, you do not have to worry about what do you call how much loop gain you have. Okay. All right. So, having seen that, now let us put this principle to some use and see some of these are circuits that we you are very familiar with, and as we saw last time, it makes sense, business sense, to sell that part as a separate building block, so that users can put their favorite feedback factor and get whatever gain they want, okay, closed loop gain they want, and that is the operational amplifier, which is basically a voltage controlled voltage source whose gain is ideally infinity, but in reality it's a large number. It's not typically if you go and pick up an off the shelf op amp, it's not uncommon to get a gain of maybe 10 power 7, 10 power 8, that sort of thing. Okay. And so it's so if the op amp is enclosed inside a negative feedback loop, we saw that the error voltage must be 0. So, the difference between the two input terminals of an op amp must be 0 if it is enclosed inside a negative feedback loop. That is the virtual short that you are very familiar with. So, now let us say you want a voltage amplifier with a gain of 2. What will we do? This is our op amp. What do we do? Well, that is very straightforward. We just identify, just stare at the block diagram. We want a feedback block with a gain of half. So, you put R there, you put another R there. So, this is VO and this is VO by 2 therefore, and this is Vi. Okay. So, this is, if the op amp's gain is infinity, then clearly this difference is 0. That basically means this is Vi, which is the same as VO by 2, which basically means that, well, the output is twice the input. This is all a very well known circuit from your from your childhood days. So, it is not something particularly new. Now, let us say you had never seen this circuit before and you wanted to figure out what the signs of the op amp must be. So, what do? Well, you did not know the signs. So, what do? You break the loop somewhere and you yank one side of the loop up here. So, what happens to this node here? What direction does it go? We let us say assume some random signs like that. So, if this goes up, that goes up. If that goes up, and for this choice of signs, this also goes up, right. And so, what comes back is of course larger than what you put in, but it is in the same direction. So, therefore, this is positive feedback, right, and therefore, that is not good as far as making a closed loop amplifier is concerned. So, what should we do? Yeah, flip the signs on the op amp. So, that becomes all right. So, now let us do another example, again something that you are most likely to be familiar with. Let us say we want an output, we want to make a current controlled voltage source, right. So, let us say we want VO is some I in times some number. So, it is a current controlled voltage source. So, that controlling that proportionality factor will have dimensions of resistance. So, that is basically what is often called a transresistance amplifier. Okay. So, again we would like to use negative feedback, all right. So, in principle what are we going to do? Let us say you are in a lab, you are given a current I in. Okay. So, let us say you are given some current I in. And I need to generate I in times R. What will I do? Okay. So, well one idea is to say, okay, well, why don't I just put a resistor here, and this gives me I in times R, my job is done. What is the problem with this? Is this a current controlled voltage source? The test for a voltage source is that you change the load resistance and the output voltage should not change, correct. So, here the idea that we first had was to take that current, pump it through a resistor R to get this I in times R. We said, now I am done, let me go home, right. So, is this a current controlled voltage source? Why? Well, if I put a load resistor, the voltage instead of being I in times R becomes I in times R parallel RL. So, therefore, it is not a voltage source. Okay. So, that is no good. So, you are in a lab now, you have a current source I in, and I tell you to produce a voltage I in times R. What all will you need and how will we go about doing this? You have a variable voltage source, okay. You want to make that the fact that you have a voltage source with a knob all right, that already means that by definition whatever RL you put, the voltage will be whatever you put there, whatever voltage Vx is there, how much ever RL you put across it, the voltage will remain Vx. So, we have solved that part of the problem. So, you have a variable voltage source with a knob, you have seen that in the lab, right. Okay. Now, I am telling you, make that voltage source equal to I in times R. So, what will I do? So, what you are telling me therefore is you generate I in times R somehow, and the easy way to generate is simply pump in the current into a resistor, right, that will generate that resistor that I in times R. Okay, tell me clearly what I should do. Okay, this is Vx, there is I in times R. Okay, all right, okay, In times R. Okay, now what do we do? Okay, you put a voltmeter here, okay, that is a voltmeter, okay. Okay, so you have to put another voltmeter here. Okay, so basically you measure, you compare Vx with V1, which is In times R. If Vx is greater than In R, it basically means that you must reduce Vx. If Vx is less than In times R, you must increase Vx, all right. And how will you increase Vx? You basically turn the knob. This much you understand, right? Clear? Okay. Is this basic idea clear, people? Okay. So what are we comparing therefore? We are comparing two voltages Vx and In times R, right. Eventually when you are done, the output voltage Vx will be exactly equal to In times R, regardless of what RL you put, correct. And therefore this is a what kind of controlled source? Current controlled voltage source. Okay. Now there is a slight problem in the sense that there are two voltmeters. Can somebody think of getting rid of one voltmeter? Yeah, well, it's pretty straightforward. We are only we are not interested in the individual voltages Vx and V1. We are only interested in their difference. So then the next thing is to say, well, we don't really need that stuff. We can just put a voltmeter between these two terminals. Does that make sense? Okay. So we are comparing two voltages, and what is the meaning of compare? We are comparing Vx and In times R. So the meaning of compare is find the difference, right? And what physical principle will you use to find the difference between two voltages? Okay, if you want to compare two voltages, what physical principle will we use? KVL. Okay, so basically we want to, so how will we subtract? Therefore, we therefore need to find Vx minus In times R. So can you tell me how we can find this quantity Vx minus In times R? So in other words, if Vx minus In times R is greater than 0, it means that Vx is too high and Vx must therefore be reduced, and if Vx minus In times R is less than 0, it means that Vx is too small and must be increased. All right. Okay. So now how will I find this quantity Vx minus In times R? So in other words, I need to compare Vx minus In times R with 0, correct. So any suggestions on how I can find Vx minus In times R? How can I generate that voltage Vx minus In times R? Yeah. So basically you recognize that you simply connect a resistance R at the output of Vx and then pull a current In like this. What is this potential? Vx minus In times R, right. And if this potential is greater than 0, you must reduce Vx. If this potential is less than 0, we must increase Vx. Is this clear? So, therefore, Vx is a voltage source which is controlled by what is V, what are the dimensions of Vx minus I in R, guys? Voltage, correct. So, that Vx is controlled by another voltage, okay. And if you want Vx minus I, and ideally we want that Vx minus I in R to be equal to 0. So, in other words, even if we sense that this Vx minus I in R is infinitesimally greater than 0, what must we do? We must kick that Vx so hard that it should go to 0. I mean, Vx should be kicked so hard in the negative direction, so that the error goes to 0. So, what comment can you make about the, so this is clearly a voltage controlled voltage source, okay. And what is the gain of that voltage controlled voltage source? What should it be? What should it be? Even if you see an infinitesimally small voltage at Vx minus I in as Vx minus I in times R, you must kick the output voltage very hard. So, what does this mean? The gain must be infinite. So, what must be the gain, what should be the sign of the gain? If Vx minus In times R is greater than 0, Vx must reduce. So, what must be the gain? Negative. The sign of the gain must be negative. So, this therefore is an op amp. And draw a more respectable picture. Does it make sense? All right. So, as you can see, the signs on the op amp come out naturally without having to guess, copy from neighbor, open textbook, all that. All right. So, what is this voltage? Yeah, I know, but we know that that's an op amp whose gain is infinite. So, what comment can you make about that voltage? That voltage is 0. So, what kind of what is the, therefore, what is the input resistance looking in here? What is the input impedance of this? So, this is our claimed voltage controlled, I mean current controlled voltage source. What is the resistance as seen by the input source? 0. Why? Because that voltage, regardless of how much current you pump in, the voltage always remains 0. So, the input impedance is 0. What comment can you make about the output resistance? What is the output resistance? 0. Why? Is there a simpler way of telling me that the output resistance is 0? Okay, if RL changes, the output is not changing, correct? Because all this current In, where is it going? Where is it going? Can it go into the op amp? No. So, it is all going through R. So, what is this voltage therefore? In times R irrespective of RL. Okay. So, therefore, since the output voltage is independent of the load resistance, it must follow that the output resistance is 0. Is that clear? All right. So, I mean, if the input resistance of this current controlled voltage source is 0, what does it mean? I mean, in practice, I mean, why do you, for instance, use a current controlled voltage source? what does that buy you in terms of, or in other words what I am saying is, if the input resistance was not 0, or rather let us now assume that we have a bad current source. What is a bad current source? Ideal current source should have an output resistance of infinity. So let us call this let's call the output resistance of this current source equal to Rx. Okay. So now what comment can you make about the output voltage? It will be same. Why? Well, one end of Rx is grounded, the other end of Rx is also virtual grounded. So the voltage difference across the resistances is 0. So what comment can you make about the current? No current flows through Rx. Okay. So In basically goes continues to flow in R. All right. So output voltage will be, this is exactly why you need a current controlled voltage source. Okay, so that you can suck out all the current from the current source, even though the current source has got some output resistance. If the current controlled voltage source was not ideal in the sense that it had some of its own, its input resistance was not 0, what comment can you make? Only a fraction of that input current In will flow into the amplifier, some of it will get lost through the output resistance Rx. That is exactly what the ideal current control voltage source ensures. Is this clear, folks? All right. Okay. Now, what comment can you, if you have a current like this, this output voltage is of course In times R. Can I replace this current source in parallel with an equivalent? Current source in parallel with a resistor is equivalent to a voltage source in series with the resistor. So what is the value of the voltage source? Pardon? This is Rx. So this is minus In times Rx. All right. Okay. So now, if you look at this picture, now it does not make any sense to call this In because there is no current at all. So you might as well call this, if I call this V in, what can I call this? Yeah, but what is V out in terms of V in? R, okay. So it is basically V in times Rx Is this correct? Minus. Okay. All right. And this is this circuit familiar? Right. So this is the very well known inverting amplifier, right, but you know now where it comes from. All right. So you try to make a voltage current controlled voltage source. All right. And the current source is bad, then it's equivalent to basically a non-invert, equivalent to an inverting amplifier. There's of course another way of deriving this, what do you call, again from first principles. Okay. So if you want V out to be the negative of V in, what does it mean? V out plus V in must be equal to 0. So you compare, you add V out and V in and compare that result to 0, correct. And how will you add two voltages? KVL of course, but how will you implement addition? Let us say you want V1 and V2, you want V1 plus V2. Can you get V1 plus V2 using only resistors? Can you get V1 plus V2 by 2 using only resistors? Yeah. So, basically if you take V1 and V2, connect both of them with connect them together through two resistors, the midpoint will basically give you the sum of the two multiplied by some fraction. Since we are only comparing it with 0, that fraction does not matter, correct. So, what I was saying was, let us say we want VO to be minus Vi, right. So, what will we do? We will find VO plus Vi. If VO plus Vi is greater than 0, what does it mean? It means V naught must, it means V naught is too high, and therefore, V naught must reduce, and vice versa. Is this clear? So, now the question is and now V naught plus Vi greater than 0 is equivalent to saying V naught plus Vi by 2 is also greater than 0. So, how will you get V naught plus Vi by 2? Let us say you have VO, you have Vi. How will I get VO plus Vi by 2? Yeah. So, basically, so this is R, this is R, alright. So, what is that voltage? V naught plus Vi by 2, and if that is greater than 0, VO must go down. If this goes up, this must be pulled down, and so what must be? It is a voltage controlled voltage source between that midpoint of those resistors and the output, and what must be the gain of that voltage controlled voltage source? Even if that voltage is infinitesimally greater than 0 or less than 0, you must kick this node so hard. So, this you must put an amplifier like this, an op amp like this, to go and kick the output in the right direction, correct. And the output therefore is going to be, since the op amp is ideal, that midpoint of those resistors is condemned to be at ground, and therefore, the output voltage is the negative of the input voltage. Does it make sense? Okay.